Design for test (DFT). Design for test enhances testability of a product, thus reducing test cost. Testing involves applying test patterns to a circuit's inputs and verifying that the expected outputs are produced. The intention is to verify that the manufactured chip performs as designed. Additional circuitry is included to improve the system's testability. Such circuitry includes elements that make internal nodes observable or that perform testing automatically as a special mode of system operation. Fault models and fault simulation. Fault models represent the effects of defects, that is faults, in a circuit and are used by a fault simulator to determine fault coverage of a set of test vectors. The simulator applies test vectors until an incorrect output results, indicating the fault has been detected. If no incorrect output is produced for all of the test vectors, the fault remains undetected by the set of test vectors. The simulator repeats the simulation for other faults and other locations in the circuit. Once all of the faults have been simulated, the fault coverage of the test vectors, that is, the proportion of faults detected, can be determined. Ideally, the fault coverage should be 100%, but for a large design, this may not be feasible. An automatic test pattern generator (ATPG) can be used to choose test vectors. ATPG is an EDA tool that analyzes a circuit and seeks to create a minimal set of test vectors with as close to full coverage as possible. Fault models. The first fault model is stuck-cut model. Stuck-cut model is a model in which an input or output of a gate in a circuit can be stuck at 0 or stuck at 1, rather than being able to change between 0 and 1. Such a fault might be caused by a short circuit to the ground or power supply. Figure shows a stuck-cut model in which an input to the AND gate is stuck at 1. For some input combinations to the circuit like B equals 1 or C equals 1, the value at the stuck node would normally be the same as the stuck-cut value. The circuit would produce the correct output and fault would not be detected. For other input combinations like B equals 0 and C equals 0, the value at the stuck node would be the opposite of the stuck-cut value. In this circuit, if A equals 0, the output value is independent of the value at the stuck-cut node, so the fault is masked. However, if A equals 1, the value of the stuck node is propagated to the output, allowing to detect the fault. Detecting the fault involves applying a combination of input values that sensitizes the path from the fault to the output and that drives the stuck node to the opposite of its stuck-cut value. A node in a circuit is observable if a fault at the node can be made to result in an incorrect output value. The node is controllable if there are input combinations that cause the node to take on a given value. Observability and controllability of nodes in a circuit determine the testability of the circuit. Second model is stuck on or stuck off. Stuck on or stuck off considers the transistor level circuits for gates and involve transistors being stuck on or stuck off. This detects faults that are not adequately represented by the stuck-cut fault model. For example, given the output driving circuit of a gate as shown in figure, a fault might cause the upper transistor to be stuck on. When the gate should be driving a high logic level, its output is correct. However, when it should be driving a low logic level, both transistors are on. This creates a voltage divider, and the output logic level is an invalid level between the valid high and low levels. A testing approach used for such faults is to measure the steady state current drawn from the power supply IDDQ to detect the increase when both transistors are on. Other models include bridging faults. Bridging faults represents short circuit connections between signal wires. Delay faults. Delay faults include the propagation delay of a circuit in longer than normal. Other type of fault is faults in storage elements. Scan design and boundary scan. Faults in registers and other storage elements are significantly more difficult to control and observe. Scan design techniques address this problem. Scan design techniques involve modifying the registers to allow them to be chained into a long shift register called a scan chain as shown in the figure. Test vectors can be shifted into the registers in the chain under the control of the test mode input, thus making them controllable. Stored values can also be shifted out of the registers, thus making them observable. The chain of registers allows to control and observe the combinational blocks between registers. Each combinational block can be tested separately. Shift test values into the register chain until the test vector for each block reaches the input registers for that block. Run the system in its normal operational mode for one clock cycle, clocking the output of each block into the block's output registers. Apply test vectors to the external inputs of the system and observe the external outputs of the system in order to test any combinational input and output circuits. Finally, shift the result values out through the register chain. The test equipment controlling the process compares the output values with the expected results to detect any faults. This sequence is repeated until all of the test vectors have been applied to all of the combinational blocks or until a fault is detected. Advantage is increased controllability and observability. High fault coverage is feasible, especially for large circuits. Test generation for testing combinational circuits can be automated by ATPG tools to achieve 100% fault coverage. Modification of registers. Modification of registers is to allow them to function as shift registers can also be automated. One approach is to design and synthesize the circuit normally, generating a gate level circuit with flip-flops implementing the registers. Then, as part of physical design, a tool can substitute modified flip-flops that have a shift mode as shown in figure. The circuit is placed normally. Finally, during the routing step, connections are made between adjacent flip-flops to form the shift register chain. Disadvantages of scan design. The first disadvantage is overhead in circuit area and delay. Modified flip-flops have additional circuitry including an input multiplexer. An input multiplexer imposes additional delay in the combinational path leading to the flip-flop input. If the path is a critical timing path, performance of the whole system is affected. Second disadvantage is the scan chain is very long. Shifting test vectors in and result vectors out takes a large fraction of test time. One of the issues is possibility of faults within the test hardware, that is scan chain. First test the scan chain, then proceed to test the internal circuits of the system. Boundary scan. Boundary scan, an extension of scan design concept, is a technique for testing the connections between chips on a PCB. The idea is to include scan chain flip-flops on the external pins of each chip. To test the PCB, the test equipment shifts a test vector into the scan chain. When the chain is loaded, the vector is driven onto the external outputs of the chip. The scan chain flip-flops then sample the external inputs and the sampled values are shifted out to the test equipment. The test equipment can then verify that all of the connections between the chips, including the chip bonding wires, package pins and PCB traces, are intact. Various test vectors can be used to detect different kinds of faults, including broken connections, shorts to power or ground planes, and bridges between connections. The success of boundary scan techniques led to the formation of the Joint Test Action Group JTAG in 1980s for standardizing boundary scan components and protocols. The term JTAG has now become synonymous with boundary scan in its basic and extended forms. JTAG, that is boundary scan, supports automatic testing of individual chips and PCBs containing multiple chips. Standardization has been managed for some time by IEEE as IEEE Standard 1149.1. The JTAG standard specifies that each component have a test access port (TAP) consisting of the following connections. The first one is test clock (TCK), provides the clock signal for the test logic. Second one is test mode select input (TMS), controls test operation. Third one is test data input (TDI), serial input for test data and instructions. Fourth one is test data output TDO, serial output for test data and instructions. The last one is an optional test reset input TRST. Figure shows a typical connection of automatic test equipment ATE to the taps of components on a PCB. Next figure shows the test logic within each component. The tap controller governs operation of the test logic. There are a number of registers for test data and instructions, and a chain of boundary cells inserted between external pins and the component core. A typical boundary scan cell is shown in the figure. Depending on the control inputs to the cell, data can flow straight through. Input data can be captured, output data can be driven, and test data can be shifted through. Input and output pins of the component each require just one cell. Tri-state output pins require two cells, one to control and observe the data and the other to control and observe the output enable. Bidirectional pins require three cells as they are a combination of a tri-state output and an input. The tap controller operates as a simple FSM, changing between states depending on the value of the TMS input. Different states govern shifting of data into the instruction register or one of the data registers, including the scan chain. The JTAG standard defines a number of instructions for instruction formats for operations that select among data registers, control the mode of scan design, and so on. There are also instructions for component-specific extensions like built-in self-test modes. The JTAG standard also defines the boundary scan description language, which is a subset of VHDL used to specify the pins, registers, and instructions implemented in the test logic of a component. We can use a BSDL description of a component together with a set of test vectors as input to ATE for testing the component and the board in which it is embedded. JTAG architecture solves two problems. First one is in-circuit testing of components in a system, and the second one is in-circuit testing of the connections between the components. Built-in self-test (BIST). Built-in self-test techniques involve adding test circuits that generate test patterns and analyzing output responses. Role of the ATE is reduced to initiating test operations, verifying successful completion. Role of ATE is reduced to initiating test operations, verifying successful completion, or if a test fails, storing any diagnostic information produced by the BIST circuits. Advantage of BIST: being embedded in a system, it can generate test vectors at a full speed of system. It can also generate multi-cycle test sequences. BIST hardware remains available during the operational time of the system. Disadvantage is larger area overhead. A system with BIST and redundant components is capable of reporting faults to a service center over a network connection. Generating test patterns. The most common means of generating test patterns is a pseudo-random test pattern generator. Pseudo-random sequences can be repeated from a given starting point called the seed. Pseudo-random sequences can be readily generated with a special simple hardware structure called a linear feedback shift register (LFSR). Figure shows an LFSR for generating sequences of 4-bit values. The sequence is initiated by presetting the flip-flops, generating the test value 4 ones as the seed. On successive clock cycles, the LFSR generates values in the sequence shown in figure. The sequence contains all possible 4-bit values except 0000. LFSR can be modified to form a complete feedback shift register (CFSR) as shown in figure, which generates all possible values. Similar circuits can be designed to generate pseudo-random test vectors for other lengths. Placement of XOR gates within LFSR is determined by the characteristic polynomial of the LFSR. Analyzing output responses. Infeasible to store the correct output response for comparison with the circuit's output response. Commonly used technique for output response compaction is signature analysis. This technique is closely related to use of LFSRs for test pattern generation, and the same mathematical theory underlies operation of both. A signature register forms a summary called a signature of a sequence of output responses. Two sequences that differ slightly are likely to have different signatures. Figure shows an example of a multiple input signature register MISR with 4 inputs from a circuit under test and a 4-bit signature. First, a logical simulation of the circuit is performed. The sequence generated by LFSR is used as input values for simulation. Output values from the simulation are used to compute the expected signature. This signature is saved for use during a test. When BIST of a circuit is initiated, either by ATE during a manufacturing test or by an in-system test controller during system operation, The LFSR generates test patterns and the MISR computes the signature of the actual circuit's output. The ATE or test controller then shifts the computed signature out of the MISR and compares it with the expected signature. If they are the same, no fault is detected. If they differ, there is definitely a fault.